Hello there, welcome to another problem session. So today we are going to talk about a couple of problems in the field of relativistic Doppler effect. Okay, so you probably heard of Doppler effect that if we observe the same wave from two different reference frames, which may be in motion with respect to each other, then the wavelength and frequency of the same waves will be different in the two different frames. So the relativistic relationship for this particular picture, you probably know this, that these are relationships. It's usually better to write using x0 and x1, x2, x3 like that. So it's like index them. This can be called x1, this can be called x2, this can be x3, and this is the time part, and you can write down x0, and x0 is a ct. So all of them have like the units of length. And you can always convert by multiplying by c, or divide this whole thing by c, and you will get what the t should be. Okay, so, but we're going to only look at the motion along the x-axis. So this we don't need to worry about converting going all the way there. And gamma is the the constant that will result from the from this v over c. Okay, so this is the dilation factor. Okay, so x0 or ct will be in this. If the frame was moving on the left, then you'll have a minus sign here and minus sign here. So depending on which way the frames are moving, you can have plus, but we're going to use this as a main way of thinking about it right now. Okay, so what kind of problems, before I do this, that in the relationship between the frequency and that this will imply that the frequency in the two frames will be related this way. So this is a kind of a final answer, but we will derive it here. But first I want to say a couple of things about problems we're going to solve. Okay, so here is a kind of problem that we will solve. So this is kind of Milky Way. Milky Way is of course not like shaped like that, but shaped like that. But over here is Earth or Sun, and this whole Milky Way rotates about the galaxy once every 200 million years, and our Sun is about 30,000 light years away from the center. So it tells you how fast the Earth or the solar system is itself is moving. So you can say it taking the Earth with it, right? So how fast the Earth is moving. This is very fast actually compared to other speeds. So there was a star here and emitted lambda. Then because you can think of this as a x-axis and y-axis, and over here you can just assume it's this instant. This is a common x prime axis. This is the moving frame, and this is the fixed frame or still frame. So it could be in the line that Earth is moving. This thing is in the same direction. Another would be a orthogonal problem will be still you have a x this way and y this way, but now it's moving the direction in which the Earth is moving and the direction in which the wave is moving is perpendicular to each other. So in both these cases it starts with the lambda. So maybe it's lambda a prime here and lambda b prime here. So the question is lambda a prime minus lambda, so one shift, and lambda b prime minus lambda, the shift. These are two things we have to figure out here. Okay, I'll say another problem. Another problem that we can encounter it's all simple problem to solve. So here is a discharge tube, and for high voltage between cathode and anode, there will be discharge, and hydrogen atoms can come very excited and move very fast. So they'll move because of thermal motion, and from there we can figure out, from this given temperature, we can figure out how fast this is moving. And is moving is going to let out some photon, electromagnetic wave, and then we can find out if it is in its frame. So this is, you can say you can say this is in a different frame than the frame in which the atom is moving. So you might say this guy is moving, the observation thing is moving this way with some speed v, and atom is emitting at lambda. The question is lambda prime. So what's the lambda prime and lambda? So that's the question here. So because we can find the v, and if you know the formula for how to get lambda prime from lambda, we can do this. So basically all of these problems hinges on finding that relationship in the other other slide. Okay, so first thing to figure out is what is the relationship like this, and also once we have f prime, we can say f prime lambda prime is the speed of light, will be same as f lambda. So we can just convert this. You can see this whole thing will become 1 over c over lambda prime equals c over lambda, and 1 minus v over c, 1 plus v over c, and the c cancels out, and so you just say 1 here and 1 here. So this will be a relationship between lambda. Given lambda and v, you can figure out lambda prime, and vice versa. Okay, so the main question is where this comes from. You can use this formula as like given to you, or suppose you forgot the formula, then there are a couple of easy ways to get it. So one is very quickly, I'm gonna do it out here and then go over that. Okay, so I took time to write it out to save time. So what I did was in the original frame, the wave will look like this with some amplitude which I just ignoring, and in the moving frame the wave will look like this. After all, this is just a plane wave. Okay, and then for to figure out what relation of this with k and omega r, and of this with k and omega r, these relationships, we can just substitute for x prime and t prime from these things we know. So this one is like you can say t, and this will be t, and then if you use the t, then this will come square here, and then if you do t prime, if you do this t prime, then the c will cancel out. So just use that, and then x prime things are combined together, the coefficient of that will equal to k prime, and that gives me this, and t prime things we collect together, and their coefficient equate to omega prime, and you get that. Now omega prime has to be this reason needs to be a little further processed, and I just go through these processing steps, and so you can, all of this is the same thing, it's just hard to write it just a compact way like that. You can see this one doesn't look like that, but numerator you can write down as 2 factors, this is square root, and denominator we just factor out, and one of the factor cancel out, and so this is the same as that. And you can use omega angular frequency omega is going to be 2 pi regular frequency in any frame, right? And that's how all of this can be worked out. So now we know these are the working relations, and these are working relations, and we can just use them to solve the problems that I presented earlier. Okay. So now how do we do this problem? We're just going to do A first, and then B. We're not going to do moving away in the other direction. Okay. And you can just try to do what that will look like. For instance, this light is moving towards this, so this wave, its frequency will go up, and this moving away, its frequency will go down. Over here we'll have to figure out what happens, what will the formula for this, which we did not derive earlier, we just derived in this case. Okay. And when I get to this, I'll just derive that also, or I'll just give you the answer for how to deal with this. Okay. All right. Let me pause and clean up here. Okay, so first thing to figure out is what's this speed v of the Earth moving with respect to the the entire universe, so to say. A fixed or a rest frame. So this is the rest frame here. So this is the rest frame. So this is the y and x, and this is y prime and x prime. So the question is how fast this thing moves. So that's v, and those things are given to us, and it's given some kind of weird unit, astronomy unit. So light year is how much distance light travels in a year. So you can see the speed will be, it's going in a circle, you see 2 pi r, and goes in a period t. The distance is 30,000 light years. So this is 2 pi 30,000. This light years, this much time at speed c. So that's the distance it must have traveled. This is in meters, the meter per second. Then you have a conversion multiply by how many seconds in a year. So year to second conversion, and this time is 210 to the 6 years, and then you can convert years to seconds conversion, and those guys will cancel out. And so if I work this out, this just becomes this is the speed. This becomes we can take this, divide with the whole thing, and let me do that. It's 1061 approximately. So that's a speed. Is not too shabby. It's pretty fast, about 1,000th of c, and so we need v over c, which is 1 over 1061, and for frequency, f prime is square root of, and because this is coming in, frequency will have to go up, so this will be 1 plus v over c, 1 minus v over c, and you can see that this is whatever the frequency is, and square root of so that's is very close to 1, but not 1, because frequency is very large. It's going to be and for this I think I got you can do this, or you can do questions about lambda. So 1 over lambda prime will be 1 over lambda is square root of so from there, using lambda equals to that, lambda prime turns out to be 6.557 angstrom. So lambda delta lambda so this 6 angstrom. That's the answer for this situation. But for this, if the wave was coming in this way, we need to work out the relationship, and I'm going to work that relationship out now. So for the perpendicular direction, a wave traveling along the y-axis, this won't be the formula. This is for longitudinal. When for this direction in which the frames are moving, and this is a wave is traveling along perpendicular direction, or the z direction you could have used, but you just use y direction. So for that, if I'm in the at rest frame, I will have cosine ky plus omega t. Let's just travel to the negative direction, then we'll plus this time. Now if we want to transform it, y will go into y prime, so this will become cosine. So we want to know what does it look like cosine in the prime frame. Okay, so we just transform it. We'll see k going to be y prime, and omega, this t will be gamma t prime, but then this is going to be an x prime coming there, so it's going to be both x and y prime direction. So plus gamma v over c square, gamma v over c square x prime. So you can see that now this is kx prime, this is ky prime, and this is omega prime. So omega prime now, so this is the transverse effect, wave in transverse direction to v. So in this case, omega prime is not this, but omega prime is gamma times omega. So f prime is gamma times f, and 1 over lambda prime will be gamma times 1 over lambda. So we're looking lambda difference, so we can just say lambda prime is lambda over gamma. So lambda prime minus lambda is we will just figure that out, and then we can lambda prime minus lambda from there. Okay, so we have a wavelength is reduced. Okay, now we can go back to the problem and just use this formula. So now for this case, we have lambda prime equals to lambda over gamma, which so we need to figure out gamma, or lambda is square root of 1 minus v square over c square. So v over c is this, so lambda is 63 is square root of 1 minus 1 over. Now this kind of calculation is you can see your calculator may actually not work very well. And because this is very small, we can do a expansion, because 1 minus half 1 over 10 61 square plus, and you can just keep that. So but this one with this is just lambda, so lambda prime minus lambda equals minus 63 times half 1 over 61 square, and this is in angstroms, so this whole thing in angstrom. So we can simplify it and just calculate and get the final answer. So this turns out to be minus 0.03 angstrom. It's very this effect is much harder to detect than this effect, because you can remember this has 6 angstrom and this is very, very small difference. Now if this was moving away, you will have a plus, and so we usually write delta lambda equals to 0.003 angstrom as an answer. Okay, so this was a very interesting problem. Let's try to just sketch out the answer to the other problem. First thing to notice in this problem is the answer is all longitudinal. You can see it's in the same direction. So this is all in the same direction. So v is in that direction and the wave is in the same direction. So here omega prime equals to omega square root of 1 minus b over c. It depends on, you know, if they're moving towards each other, then the frequency will go up. So if we go up, you'll write this 1 minus b over c. So so I'll just need to get v. How do we get v? Well, v will be we can do half mv square is going to be 3/2 Boltzmann constants T in degree Kelvin, temperature in Kelvin. So from there, and all this given, you can get a V, and you can write that. So if you want to get a V over C, this will be C square, and so V over C will be half cancel out 3 kBT over MC square. So I will work out the numerical value for that. I'm not going to do it, but I suggest you work that out, and from there you can figure out f prime will be like that. So you can get f prime minus delta f. Again, you can you have to be very careful when you're doing numerical calculations with very small numbers or very large numbers. Your calculator will saturate, and so best is to do maybe if your V over C is very small, then you can expand these kinds of things. So like 1 over 1 plus x can be 1 minus x plus x square minus x cubed, like this. And x is small, then you can just drop this. So this will be almost identical to that. And if you like 1 plus x over a, then x is small will be 1 minus ax. So you have other terms, we dropped it. So sometimes using a expansion, Maclaurin expansion or Taylor expansion about small x at x equal to 0 is helpful if x is small, rather than directly plugging in the calculator. With that, I'm going to stop here. The video is already very long. And just will remind you to subscribe to this channel if you like this kind of explanation. I appreciate like buttons that you put. I go check. If you have some questions, you can leave comment, so I'll try to answer that. Or check out my this website also, where a lot of these things are covered in greater detail. Talk to you later. Bye.